Hello and welcome. In this video, we'll be taking an in-depth look at the guidance algorithm used by NASA's MSL mission to land on Mars. We will also be implementing it in Python. Since this is kind of a long video, here are some timestamps if you want to skip ahead. Flying to Mars is not easy. Landing there is even more difficult. After 6 decades of trial and error, humanity now has 14 spacecraft on or around Mars, 8 in orbit and 6 on the surface. Unlike on Earth, the Martian atmosphere is not thick enough to quickly slow down an inbound spacecraft before it hits the ground. But at the same time, there is enough of it to create aerodynamic heating that could cause the spacecraft to burn up, especially if you use the wrong units in your software. Mars is also far enough away from Earth that any robotic spacecraft attempting a landing must be able to do so autonomously due to the significant communication delay. While initial missions focused on just getting the vehicle down to the surface safely, more recent missions have included sophisticated landing systems that allow for pinpoint landings near targets of interest. This is possible thanks to a guidance system that actively maneuvers the spacecraft during entry to account for disturbances caused by factors such as wind, atmospheric uncertainties, and navigation errors. In this video, we will take an in-depth look at the entry flight of NASA's Mars Science Laboratory mission that landed the Curiosity rover on Mars in 2012. We will look at the math underlying the guidance system and also implement and simulate its flight using Python. MSL's landing on Mars happened in a series of distinct phases. The focus of this video will be on the entry phase, starting from the entry interface at around 135 kilometers altitude and ending just before the parachutes were deployed once the spacecraft had slowed down to around 600 meters per second. The supersonic parachute deployment and the subsequent sky crane maneuver is outside of the scope of this discussion. Prior to MSL, no Mars entry system has utilized a real-time guidance algorithm to autonomously adjust its flight path within the Martian atmosphere. The Mars Pathfinder and Mars Exploration Rover missions flew ballistic entry trajectories. This means that the spacecraft did not maneuver in the atmosphere and had limited control over its flight path once it was within the atmosphere. While the Viking missions flew lifting trajectories, they did not utilize aerodynamic lift to adjust the vehicle's flight path in real time. Instead, they used the lift to maximize flight time and allow for appropriate deceleration in the thin atmosphere of Mars. This meant that in all these cases, the probable landing zone covered a really large area and pinpoint landings were not possible. For example, the Mars rover Opportunity had a projected landing ellipse that was almost 150 kilometers long. MSL and last year's Mars 2020 mission that included the Perseverance rover used a guidance algorithm that was originally used by the Apollo command module during re-entry when returning from the moon. MSL represented a major advance in autonomous entry guidance technology when it actively used aerodynamic lift to correct its flight path in response to external disturbances. Because of this, MSL's projected landing ellipse was only 20 kilometers long, and it landed the Curiosity rover just 2.5 kilometers from the planned landing site. The MSL aeroshell was a blunt cone, covered by a heat shield on the side facing the incoming airstream. Prior to entering the Martian atmosphere, the spacecraft jettisoned some ballast masses, which created an offset in its center of mass. This caused the spacecraft to change its pitch angle and present a small angle of attack to the airstream. In this configuration, it was able to produce a small amount of lift with a hypersonic lift-to-drag ratio of around 0.24. At hypersonic speeds, even this relatively small amount of lift is enough to precisely control the spacecraft and guide it to a targeted landing zone. MSL controlled its trajectory by banking left and right, similar to how an aircraft banks while turning. When an airplane banks, the lift vector is pointed away from the vertical direction, and the extra horizontal component of lift causes the aircraft to change direction. This also has the consequence of decreasing the amount of lift force counteracting gravity. In an airplane, the pilot accounts for this reduced vertical force by pitching the airplane slightly up to increase the total amount of lift, or even by increasing the engine power during steep turns. However, unlike a turning airplane, for an entry vehicle like MSL with no source of thrust, the reduced vertical lift results in an increased rate of descent and steepens its trajectory. If the guidance algorithm estimates that it is going to undershoot the targeted location, decreasing the bank angle will decrease the rate of descent and bring the trajectory back to its original point. Similarly, if it is going to overshoot the targeted point, it can increase the bank angle and descend faster. Going deeper into the atmosphere results in higher drag, higher deceleration, and a shorter ground track, while staying higher up results in lower drag and lower deceleration and a longer ground track. Going higher or lower in the atmosphere also has implications for heating. By using this strategy, MSL's guidance system was able to precisely guide itself to a target location. One side effect of using this method is that the spacecraft ends up flying off track laterally due to the horizontal component of lift. The guidance system counteracts this by reversing the direction of bank angle from time to time, effectively performing a series of S-turns. However, we will be ignoring this cross-range guidance component in this video and focusing purely on the downrange guidance using a two-dimensional flight model. When a SpaceX Falcon 9 lands back on a drone ship or landing pad, its onboard computers are constantly computing new optimal trajectories that minimize the landing error and then using these results to guide the rocket. However, this was not possible in the Apollo era due to limitations in computer hardware and software of the time. The Apollo guidance computer ran at a clock speed of 2 MHz and had just 4 kilobytes of memory and 72 kilobytes of storage. So the Apollo guidance algorithm was built to run on this hardware. It was designed in such a way that the bulk of the computation was done on more powerful computers on the ground. These computers calculated a reference trajectory based on a reference bank angle profile determined by the engineers. This data was then transmitted up to the spacecraft just prior to entry for use by the onboard software. The actual computation requirements in flight were minimal compared to the work done to generate the reference trajectory. Even though MSL flew with much more powerful computers than Apollo, the guidance algorithm retained the simplicity of the original version. Next, we will look at the math behind the Apollo entry guidance algorithm used by MSL. So before we can devise a guidance methodology, we need to know how the vehicle flies, how it interacts with the atmosphere of Mars while it undergoes entry. And for this, we need to build up something called the dynamic model of the system. In this case, we'll be using a 2DOF or 2 degrees of freedom dynamic model. This means that we will be modeling the spacecraft motion in just 2 dimensions, altitude and downrange motion, and we'll be ignoring the cross-range motion of the spacecraft. So there will be 4 states in this 2DOF model, effectively specifying the position and velocity of the vehicle in 2 dimensions. H refers to the altitude of the spacecraft above a certain reference level. Now on Earth, this would be the sea level. On Mars, there's a previously agreed upon standard level that is used as the reference. S refers to the downrange distance flown by the spacecraft as measured along the surface. V is the magnitude of the velocity vector or the speed of the spacecraft while it's flying. And gamma is the last state, and that is the flight path angle. And this is the angle between the local horizon line and the velocity vector. It's important to note that this is not the pitch angle, and it has nothing to do with the orientation of the vehicle. All it says is whether the vehicle is flying up or down with respect to the local horizon. So if gamma is positive, that means the altitude is increasing. If gamma is negative, that means the vehicle is falling or the altitude is decreasing. Now that we have defined the states, we need to define the equations of motion. These are differential equations that define how the states evolve with time. And these are the equations of motion for the 2DOF dynamic model. D over m refers to the drag acceleration acting upon the spacecraft. It's defined in terms of rho, the atmospheric density at the current altitude, and beta, the ballistic coefficient of the spacecraft. Rho itself is defined using this exponential model as shown here. The parameters for this model are rho 0, which is the density of the atmosphere at the surface, and h, the scale height, which defines how quickly the density drops off with altitude. The ballistic coefficient for MSL was 120 kilograms per square meter. Beta is a measure of how much the vehicle is affected by the atmosphere. The higher the value of beta, the less it is affected. Next, we have L over m, which is the lift acceleration. And we obtain this by multiplying the drag acceleration by the lift to drag ratio, or L over d. In the entry configuration, the MSL aeroshell generated around 0.24 lift to drag ratio. U is the bank angle of the spacecraft, and you can see that it directly affects the lift force acting on the vehicle. Next, we have these parameters G and Rm, which are some properties describing Mars. So here G is the acceleration due to gravity, and we consider this to be a constant because in the range of altitudes that the vehicle is going to fly through, there isn't going to be much difference in how much gravity there is. And Rm is the radius of the planet. So now we have the dynamic model defining how the spacecraft is going to fly during its entry. Next up, we will derive the control policy, also called the control law. This is a mathematical expression that tells us what bank angle the spacecraft should be flying to achieve some goal. For Apollo guidance, what we are trying to do is to find a constant bank angle command that will minimize the range error between a reference trajectory and the actual trajectory. So what exactly is this range error? Well, let's say we have this reference trajectory. This is something that NASA engineers would have designed on the ground based on where they expect the vehicle to be when it starts entry. And let's say that it starts at time t0 with state x0 star and ends at the terminal altitude with state xf star at time tf. And it does so while traveling downrange a distance of RF star. Now, in the real world, when the spacecraft actually flies this procedure, it may start at state x0 that is different from x0 star due to, say, navigational uncertainties. After flying for time tf, it reaches a different end state xf at an altitude of hf. So if this trajectory was propagated all the way to the correct terminal altitude, it would have traveled a distance RF. So the goal of this guidance algorithm is to command a bank angle such that RF is equal to RF star. This is solved by applying something called calculus of variations. We define a functional J as equal to the range RF. And what we are trying to do is to find a constant value of bank angle U that will cause the spacecraft to travel a range RF star. Or in other words, we want to keep J at RF star even if the trajectory gets perturbed as shown. And we have to do so while constrained by the equations of motion as given by x dot equals f and also the boundary conditions. This is a type of optimal control problem where we are trying to find a control signal that results in the stationary value of a functional. So when we apply calculus of variations, this problem gets converted into what is called a boundary value problem. This involves some new mathematical entities called costates, one for each state as given by lambda h, lambda s, lambda v, and lambda gamma. They each have their own equation of motion and boundary condition as shown here. We will also introduce another variable, lambda u, with the given equation of motion and boundary condition. And when we solve this boundary value problem, It is set up in such a way that it'll give us the optimal solution for the original problem. I obviously skipped a lot of steps here. The full details of how this is derived could be an entire video on its own. So I have the full derivation with all the steps in the accompanying blog post linked in the description. Please read it if you're interested. The derivation also gives us the control law, which tells us the exact bank angle that the spacecraft should be using. And that's what we'll be looking at next. The control law, or control policy as it is sometimes called, tells us what control signal, in this case the bank angle, should the vehicle command in order to fly the optimal trajectory. And here is the final expression we derive for bank angle. It is the sum of u star, the reference bank angle used to generate the reference trajectory, and delta u, which is the correction that we compute to account for the deviations in the spacecraft's trajectory. Delta U expands into this giant expression. Now, again, if you want to learn more about how this was derived, check the link in the description. While this may look complex, it is pretty simple once you break it down. All the terms highlighted in red have stars next to them, which denotes that they're all to be computed with values from the reference trajectory. And also, we find that lambda s has a constant value of 1 and can thus be ignored. The rest of the red expressions are all computed on the ground along with the reference trajectory and transmitted up to the spacecraft. So they can be replaced with these terms F1, F2, and F3. The remaining terms in yellow are the error terms. These are telling us how far away the spacecraft is from the reference trajectory in terms of range flown, the altitude rate, and the drag acceleration currently sensed by the spacecraft. If you're familiar with PID controls, this may look very familiar to you. The values F1, F2, and F3 are acting like gains that are multiplied with the error terms. You will also notice that all of these terms are defined with respect to V. This is because when we actually implement the guidance, we'll be using the current speed of the spacecraft to find out what data point in the reference trajectory we are supposed to be using. So now that you have this, all that the guidance system needs to do is get the current state of the spacecraft from its sensors, look up the data in the reference trajectory that is corresponding to the current state of the spacecraft, perform this computation, and then command a bank angle equal to u star plus delta u. And you should also note that u will also be constrained to be not more than 180 degrees. And one other factor is that when NASA originally tested this in simulations, they found that the response for this controller was pretty sluggish. So what they did is they added this value k called an over control gain, which essentially magnifies the effect that the guidance controller has. In MSL, k was set to a value of 5. And when we implement this in Python, I'll be showing how the performance of the guidance system varies based on the value of k. All right, now let's get to actually implementing this guidance algorithm in Python. So before we start, you need to understand what is numerical integration. If you already know this, feel free to skip ahead to where we actually write some code. Here, I'm looking at the help page for the SciPy package. And within SciPy, we have scipy.integrate, which has a bunch of functions that let you integrate differential equations. Of these, we'll be focusing on the one called solve IVP. The documentation is pretty self-explanatory. You pass in a function that defines the equations of motion. You pass in tspan, which is essentially a tuple with two values, t0 and tf. This tells the integrator that you want to integrate from t0 to tf. And then we pass in y0, which in our terms, it would be x0. That is the initial condition for all the states that you're integrating. Apart from this, the only one you need to care about is t-eval. So this tells the integrator what points of time are you interested in seeing. So for example, if you want to integrate some states from time 0 to time 10 seconds, and you want to know the state at every second, so time equals 1, t equals 2, t equals 3, etc., you would pass in an array here that is having the numbers 0, 1, 2, 3, etc. up to 10. So this lets us specify how granular of an output we want from the integrator. Now that we have that, let's go to the notebooks. So I do have a notebook here called Basic Simulation that you may want to go through, that sort of sets up the simulation by itself with no guidance controller, just to see what it looks like. Now let's move on to actually generating the reference trajectory. And here we have the reference bank angle function. This profile was something that I got from this paper, which is Guidance Design for Mars Smart Landers using the ETPC. And this is a really old paper, but this is basically the concept that was used for MSL. And this is the bank angle profile, which is given with respect to velocity. And I essentially replicated that in Python. As you can see here, it matches up with what we have in the paper. And once we have that, we need to define the equations of motion. These are the same ones that I had in the previous section of the video. And so we define that. Then we define the entry conditions, which is the altitude, velocity, downrange, and flight path angle, and the model parameters. And we also define this terminal velocity. So this is essentially saying where we want the integrations to stop. So I picked 600 meters per second speed, which is where the parachutes were supposed to be deployed after entry. And so I used the simutils. Now simutils is just a simple wrapper over solve IVP that I wrote to make some of the things easier to pass in. So for example, I can actually pass in a stopping condition, which I called altitude stop event for some reason, even though it is more general. So you can essentially pass in a condition saying, I want to stop on variable number 2, which is velocity, and with a value of 600. So once we run that, I do a preliminary plot to verify that it makes sense. So this is what's called a phase plot or an HV plot. So here we have altitude on the y-axis and velocity on the x-axis, and you can see that it drops down almost vertically, and then once we hit some atmosphere, we start slowing down. So the next step in the reference trajectory computation is to actually calculate the co-states. Now, if you remember, the co-states were supposed to have their own equations of motion, and I never expanded them. The reason for that is computing them by hand is really an error-prone method. So instead, what we do is I have this notebook, Derive Co-State Equations, where we'll actually derive these using SymPy, which is a Python package. And all I have here is F, which is the original equations of motion for the states. And I define a bunch of variables called the lambdas and X. And then we do derivative of F with respect to X, and we do that for each X. And that way we get the co-state equations for the co-states corresponding to each state. Similarly, I defined something for lambda u, which was that extra co-state that was added as part of the derivation. So once we do that, we get these nice expressions that I can directly copy paste into Python code. Now going back in here, I have those equations set up in here. Now if you notice, I have lambda h, v, and gamma. I don't have lambda s. And the reason for that is lambda s dot is 0, which means that this is essentially a constant value, and the value is 1, as you saw from the previous section. The rest of the equations are the same. We still need to propagate the states alongside the co-states because the co-states do depend on the states. When we go to actually propagate this, we need to propagate it in reverse because you remember we have boundary conditions at the terminal point for the co-states. So we start at the terminal point and we essentially run the time in reverse. So if you can see, the time span that I pass in is TF and then 0. That is telling the integrator that we want to integrate in reverse. We also pass in the terminal conditions of the states that we got from this propagation. And then we run the integrator, and that's it. So we have the co-states, we have the states for the reference trajectory, and now we just need to store it. So here I have something that'll store the data into a file called Apollo data vref. You can look into this code if you want to know more as to how it works. Now moving on to the actual guidance system itself. So here I have the Apollo Guidance Bank Controller implementation. And to start off with, we pass it some reference data. So this is the data we generated in the previous notebook. We also have the same reference bank angle function here. And here we have the closed loop Apollo guidance implementation. And to start off, we compute the reference bank angle, and then we check, are we actually in the atmosphere? So is the drag acceleration greater than the minimum, which is 0.5 Gs? And if so, we continue. If not, we just return to reference bank angle. Once we get past that, we look at the reference data and we figure out, okay, what is the data that corresponds to my current speed? And that's in this function. If you want to know how that works, it's all in this Apollo utils file. It's pretty simple. It just looks at all the rows of data and figures out which one is closest to the velocity of the spacecraft. Then we load all of these pre-computed values of F1, F2, F3, drag acceleration, and altitude rate. And then we compute the correction to the bank angle and return that value. We also set some limits on phi so that it doesn't exceed 180 degrees. So now that we have an implementation for the guidance algorithm, here I have a sort of sanity check to make sure that we didn't mess up anything. And the way we do that is by applying this closed loop guidance controller to the reference trajectory. And if everything's working, there should be no deviation from the reference trajectory at all. And that is in fact what happens here. Next, we set up what is called a Monte Carlo simulation. And what we do here is we take a bunch of parameters that we want to introduce errors into. So here we have the ballistic coefficient, the lift to drag ratio, and the entry flight path angle. And we create a bunch of random deviations in that based on these parameters that we have. So we have a 5% 3 sigma variation in the ballistic coefficient, 8% in the lift to drag ratio, and 0.6 degrees for the entry flight path angle. Then we essentially simulate the trajectory however many times we want to and compile the results. So now we will actually do some Monte Carlo simulations for a bunch of different cases. So first we will do the simulation with no controller, that is essentially always flying the reference bank angle regardless of what is happening with the vehicle. Then we'll fly the Apollo guidance with an over control gain of 1, and then we'll run the same thing with an over control gain of 5. And we are going to run this for 2000 iterations, so this will give us a decent spread in the random variables that we are simulating here. All right, now that we are done with the simulation, let's see what the trajectories actually look like. So here I'm plotting the bank angle that is resulting from the over control gain of 5 against the velocity. And it sort of looks like this weird insect. But what is happening here is essentially the controller trying to bring the vehicle back on track. So the red line is the reference bank angle, and all the blue lines are the bank angle values commanded by the controller on different iterations based on different errors. So another thing we can look at is the footprint. So this is the spread in the downrange distances once the vehicle actually arrived at the parachute deploy altitude. So as you can see, the open loop one is way off with the spread of almost 87 kilometers. And once we add in the controller, we bring it down to 27. But once we bring up the over control gain, we bring it all the way down to just 13 kilometers. Now I can save the results here using the pickle package. And then if we go on to this notebook, we can do some post-processing and see what some of these values look like. So here I'm plotting the downrange spreads. As you can see here, we have a peak at around 540 kilometers of range flown, and then the spread goes almost all the way to 580, if not more. And now once we add in the Apollo guidance algorithm, we tighten the spread quite a bit, and it only goes out to around 550 on one side and 525 on the other side. Once we put in the over control gain, now it gets even tighter. And there is this one outlier over here that's sort of skewing the whole thing. So to get rid of outliers like this, we can look at the 3 sigma spread. So that's essentially looking at where is the 99.7% of the trajectory is landing at. So if we do that, we can see that it sort of discarded this weird outlier, and the closed loop footprint is just 6 kilometers for the Apollo guidance controller with an over control gain of 5. So that shows that the controller works. And even with a bunch of errors added in to the initial conditions of the trajectory, we were still able to get within 6 kilometers of the targeted point around 99% of the time. All right, and with that, we have reached the end of this rather long video. If you stayed till now, well, thank you very much. And let me know in the comments below if you have any suggestions, questions, or any other comments. Thank you.